Alright, so this lesson is about the special angles on the unit circle. This part is not notes, but if you really want to get it, I won't stop you from getting it later. Hopefully if you did what I asked you to do, in exercise 5C question 3, you would have noticed in the PDF I put a little rectangle saying you must do this, okay? And why? Because that question paid particular attention to these two numbers, 1 on root 2 and root 3 on 2. In that lesson previously, because I wasn't here to teach you, it would have been unclear why those are important. Today's lesson is to show you why these you're going to encounter next year and then the year after that, okay? You're going to see why those are special, okay? And it relates to the special angles on the unit circle. What are those special angles? They're angles that are 45 degrees, which is pi on 4, or multiples of 45 degrees. So 135, 225, etc. Not 90 degrees, and I'll explain to you why we're ignoring 90 degrees and 180 soon. And also the other special angles are 30 degrees, which is pi on 6, and any multiples of that. So 60 degrees, once again, ignore 90 degrees. Then 120 degrees, 150 degrees, ignore 180. Why are we ignoring 90 and 180? Because I already taught you that in the first lesson of the unit circle. That's 1, that's 1, that's negative 1, that's negative 1. The angle 0 degrees, 0 radians, what's the sign of it? How far has it gone up or down if this is my direction? 0. Good. You got that from the first lesson. What's the cosine of it?
1.
1. 90 degrees. What's the sine of 90 degrees? What's the cosine of it? Good. That's why we're ignoring 90 degrees and 180 degrees, because they involve 1 and negative 1. What's the cosine of 180 degrees?
Negative 1.
Good. And what's the sine of it? Good. What's the sine of, what would this be?
Negative 1.
Negative 1. What's the cosine of it? And then back. So any multiples of 90 degrees, which is 90, 180, 270, etc., it's all going to involve 1 and 0, which we established in the first lesson. That's why we're ignoring those. We're doing, basically this lesson, we're doing the stuff in between. That's what we're doing today, okay? So move that out of the way. It's not part of your notes. So we start off with multiples of 45 degrees, which is pi on 4. This is where the notes start. So I'm going to take you on a journey here. This is like a proof, similar to something that you'll do in methods. Let's consider quadrant 1 of the unit circle, so the top right. Okay, is this an effective drawing of the quadrant 1? Mm-hmm. P is a point on the unit circle up here. OP is a line. How long is OP going to be?
1.
1, because it's a radius. And it joins the origin and P. Is there any issues with that so far? OP is at 45 degrees, so pi on 4. Angle to the x-axis, which is what I've tried to draw. It's not going to be exact because I'm not using a grid here. A line is drawn down vertically from P down to the x-axis at x. So do you agree that a triangle is formed here? Mm-hmm. If this is drawn vertically, what angle would this be?
90.
90 degrees, so I'll indicate that. So angle POX, so this angle is 45 degrees. What angle must OXP be? You just told me, because I drew it 90 degrees. OPX must therefore also be what? It must also be 45 degrees. Why? Because of the rule, angles in a triangle. Just a reminder, if like an upside down, if the triangle is pointing down of these 3 dots, that means because. If it's pointing up, that means therefore. Okay? Why? Because angles in a triangle add up to 180 degrees. 180 degrees, take 90, take 45, leaves you what? 45. Mm-hmm. Okay? So I haven't made up any rules here. This is all stuff that you've done before. Therefore, what kind of a triangle is OPX based on what we've just said? What kind of a triangle is it that has the same base angles?
Isosceles.
Isosceles. And because it's isosceles, these two base angles are the same. What can I say about these two sides of an isosceles triangle? Same length. Therefore, OX, this side, must be the same length as which? OP or PX?
Yes.
So no one disputes what I've just talked about, okay? We constructed a little isosceles triangle there, they're all 45 degrees. So if I let OX equal PX, which is just proved, and if I call that A, if I call this A, what must this be as well?
A.
That's A2. According to Pythagoras, and why does Pythagoras apply to this triangle? Because it's right angled. A squared, one of the legs, plus the other A squared should equal the hypotenuse squared. Does anyone dispute that? Okay? So, how many A squareds do I have there? 2. So 2A squared is equal to, what is 1 squared? 1. What's 2 doing to A squared?
Multiplying.
Multiply. So what is the opposite of multiplying something by 2? Dividing. So A squared is equal to 1/2. What's the opposite of squaring something? Square root. So A is going to be square root of a whole half. Why am I ignoring the plus and minus that we practiced last week? Think about, yes? Does it make sense to have a minus length?
No.
Yeah, and it's in quadrant. No. Well, here we're using Pythagoras to measure how long something is. Can I have a negative length of something? That's mainly what it is, all right? What does this cancel down to? Root 1 over root 2. What is the square root of 1?
1.
1 over root 2. So what can I say about this? This length A is equal to 1 on root 2. This length A is also equal to 1 on root 2. Please note that A is both the sine and cosine. It's how far you went across. It's also how far you went up. So you can see, hopefully, in my illustration here, can you see that the angles that are multiples of 45 degrees, pi on 4, they're all going to have sine theta and cosine theta of what? 1 on?
Root 2.
1 on root 2. So if I looked at this, that's 45 degrees. How tall is that?
1 on root 2.
How far across have I gone? How far have I gone left?
Negative 1 on root 2.
See? Okay. How far have I gone down to go to 225?
Negative 1 on root 2.
See? So hopefully you don't actually need to draw that whole bloody circle with the flower of all of the angles. Okay? Because if you get how it works in this one quadrant, it applies the same that way. It's just negative horizontally. It applies the same down this way, but negative vertically. Yeah? Now, I'll do multiples of 30 degrees, which is pi on 6. It's slightly more complicated because the angles are not as nice. Let's consider the same quadrant of the unit circle. P's on a point again. How long is OP going to be?
1.
1. OP is at an angle 60 degrees. And that's the first weird thing, but let me tell my story. Okay, I'm telling you about 30 degrees, but why is he talking about 60 degrees? Let's sort that out. A line is drawn from P to N. So that point down to N, which is at 1, 0. How long is ON going to be?
1.
Unit 1, because it's a radius. So we've got a triangle here. ONP is what kind of triangle?
Equilateral.
Don't skip a step.
Okay,
We
sorry.
don't know that yet. What's the only thing that we know? How long is this going to be?
1.
How long did you just tell me this one was?
1.
So the only thing that we know right now is it's a specific kind of triangle. What kind of triangle has 2 sides the same?
Isosceles.
Good. So that's all we know so far. If triangle ONP is isosceles, well, what can we say about this angle here, OPN, and this angle here, ONP? They should be the same, shouldn't they? Because they're the bottom, they're the base. Okay? What must these 2 angles total up to? How many degrees in a triangle? 180. How much of it has been used up by this already?
60.
So how much is left over?
120.
But didn't you just tell me those two angles are equal? So what? Two things that are the same. 60. So, like our friend said, that I don't want to say because I don't want to do a sick edit on YouTube again. ONP is actually what kind of a triangle? Equal like? Can you see why I just stopped that though? Because we didn't know that yet.
Right.
The only thing that we knew is those two sides are the same. Okay? Now we've built up an argument to say that it's equilateral. Now if I draw a vertical line down from P to the axis, so if I went down here, okay? If it's vertical, what can I say about the angle formed here?
90 degrees.
90 degrees. Triangle ONP is equilateral. The line PX down to here is going to bisect this. What does bisect mean? Cut in half. So, if I've cut this ON in half, OX must be the same as NX. And if the whole thing is 1, how long must 1/2 of it be?
0.5 or
Which is, Okay? See how this is more involved? Why? Because we're not at this, at that 45-degree triangle yet. But I want to tell the story so that you can see where these numbers come from, okay? If we look at the right angle triangle OPX, so we're looking at this right now. If I let PX be A, so I've called that A, how long is OX going to be?
1/2.
1/2. Okay, let's do some Pythagoras again. By Pythagoras, 1/2 squared plus A squared is equal to 1 squared. Now, like I said, assume knowledge. You have to be able to multiply fractions. So it's the top by the top, bottom by the bottom.
Yeah.
So 1 times by 1 is going to be 1. 2 times by 2 is going to be
4.
plus A squared. And what's 1 squared?
1.
1. If I want to get rid of a quarter, what's the opposite of positive a quarter?
Negative a quarter.
So what's going to be left if I take a quarter from this side here?
3/4.
Good, you're going to have A squared is equal to 3/4. What's the opposite of squaring something? Square root. So A is going to be root of 3/4, which is the same as root 3 on root 4, which is the same as, what is the square root of 4?
2.
2. Can you see where that number suddenly popped out from that I asked you to envisage? Okay. Note that A is equal to PX is the sine of 60 degrees, so this is root 3 on 2. And OX is the cos theta. So what can we see? When it's 45 degrees, the only lengths that I care about is 1 on root 2. But are there a couple of different lengths that I worry about here? You've got 1/2 and you've got root 3 on 2. Now you're telling me, so you still haven't told me about what 30 degrees is. You showed me about 60 degrees. What's this BS about 30 degrees? Well, do I have a triangle here?
Yep.
Yeah. Do I have a circle? Can I rotate a circle?
Yes.
If I rotated that down to be, if I place the middle of that triangle here, this is 60 degrees because you told me it was equilateral, right?
Yes.
So if I place that circle here, that triangle or pizza slice here, how many degrees would this be?
30.
30 degrees. And based on, we just worked out that this was 1/2 to the right. How far up would it be?
1/2 up.
1/2 up. And how far across would it be?
Root 3 on 2 across.
Okay. So it all applies the same. So how far is this? This is 1/2. How tall is this? That's root 3 on 2. If I went this direction, how far left have I gone? -1/2. I'm still up by root 3 on 2. Okay, that's where those numbers come. So that's the special angles of the triangle. I'll finish the recording there.